Ladies and gentlemen, it's a pleasure to be here. And I'm wondering, what does a physics professor do on the stage of a tech conference? So we'll find out in 15 minutes less, right? There is a little Sheldon Cooper in me, right? I'm a professor of theoretical physics. When I enter a lab, I have to keep my hands behind my back. Otherwise, I'll break something. But there is a fundamental thing in physics, which is our job when we have to rise to the task of compiling the vision, which you've just seen in Bob's talk, in Andrew's talk, into the physical reality. And the thing with the physical reality is that it's ultimately stubborn. We have only one assembly language, only one machine code from which we have to build a bridge towards this bright vision that has been painted by our distinguished mathematical and computer science colleagues. So what I'm going to do, I'm going to first explain the thesis that kind of convey a feeling of why is it so that quantum hardware as an innovation area, quantum hardware as the area from which we're expecting the most miraculous breakthroughs is hard. And then I will pivot towards my favorite quanta, which I won't stay shy. Those are electrons, although this is a photonics section. What's good for photons may be good for electrons, and the other way around. So here are just some pictures from the news, right? The bottom ones are the quantum processing chips from Google with IonQ, photonic platforms. The top one is actually from quantum supremacy demonstration in China. And then the top right are my favorite ones, electrons in cold chips. Same electronic chips you have on your devices, but made to work in the quantum regime. So, first thing you need to pay attention to when looking at a particular quantum technology is who are your heroes? Who are your main actors? We can have light, we can have electrons, we can have this magic smoke, magic liquid, superconducting condensate trapped into cold resonators where only two states are available. Or those could be natural quanta of matter, which are electrically charged, can be suspended in the vacuum. And each platform brings with itself its own combination of strengths and weaknesses. And there is an ecosystem around where if you have beaten some world record, you may suddenly gain an advantage in an area which doesn't have anything to do with, say, quantum computation, or even with the quantum superposition properties of your main actors. But it opens some possibilities which we have not thought of before. So there is also these branching opportunities in quantum technologies which are real, which are much shorter paths to the market, and they have to be taken together as a general strive towards quantum computations. So I need to answer my question. Let me answer that in terms of a very Latvian thing. So you pick your actors. Suppose each of those dancers is a photon or an electron. And you have to choreograph this precisely mathematically prescribed dance, which is prescribed by Andrew's algorithms, or by Bob's pictures. But there is a thing about those wires and spiders. They are super shy. So the difference between what you see on the screen and the difference between choreographing in an exact manner billions of bits in your conventional chips is that for the quantum magic to start working, you have to set up your dancers and then tell them, go, so that they perform their dance with no one else watching. And by that I mean no one. Any interactions with anyone else except the prescribed partner will lead to noise. And what you'll get at the end of the computation will be just senseless noise. So this need to choreograph things in a precise manner and at the same time keep them completely isolated for any other single quanta is what makes the true quantum technologies really challenging. So now I'm going to tell you little stories about my favorite partners, as I told you, electrons. And then I thought, what else can I say about myself? Who am I? Who else am I except for a professor? at the university. And then I realized who I am. I'm a gun designer. So one of my most successful theories, actually very simple, and I specialized in high-precision, high-speed guns. We're talking about billions of bullets per second with less than 10 misfires. And those guns, they're electric guns, because we use electric field to accelerate our bullets. And the bullets are smallest possible bullets in the world. Those are elementary particles, quanta of electricity. So that's kind of a dense academic slide. On the left side is our kind of main practical achievement of this area. That's been a development, of course, in nanoelectronics. And around 2010, we've realized what has kept the previous designs from performing at the top-notch level. And the lightest elementary particle being the electron is what those guns, or on-demand electron sources, produce. And you would think, who needs such world records? Maybe it's for Guinness World Book of Records. Well, turns out that who are interested in the most accurate sources of current are the entities responsible for the most accurate measurements. National Metrology Institute. So if you go to the, say, US National Metrology Institute and watch the picture for the electrical current standard and its future, it will show you our design and will explain how it works. And the idea here is that all quanta, exactly unlike the dancers on the stage, are identical. And the new definition of the fundamental system that underpins all measurements, the SI system, relies on the electrical charge being this exact number, which is manifested in this reality by a single electron. Things are being developed in that direction. So those devices have become, in the region of low currents, more accurate than any other way of measuring currents, like measuring volt and divided by ohm. The uncertainty of these sources is better than anything else. And that's one thing in pushing the envelope of quantum. Once you are where nobody was before, you start to notice things which you didn't know are there. So in this fundamental metrology direction, I'm kind of proud of our latest work, which also includes Andris Ambainis as a co-author. And that's the thing. If you have the proper mathematical mind on your team, that they can see the level of generality, which is not accessible if all you have is to think about all the millions of practical problems. So physicists talk to your mathematician friends, and then we have a theorem which sets the bound on the maximal possible error and allows this quantum standard to be self-referenced, so that you not only guaranteed a certain number of less than a certain number of errors per second, you can also certify that value without any reference to other standards. And yeah, so what that particular paper is about is that practical proof, experimental proof, done in Germany on the general theory of errors. And all it took was one seminar at the Quantum Algorithms Group with the best experts in random walks. It turned out random walks also apply to this particular problem, which is not related directly to quantum computations. And this same thing is happening also with other directions which go for the big thing, right? For secure quantum communication or for the computation. And two examples are the cosmic ray particles hitting the chips which are doing quantum computation and causing ultimate havoc. There was a last year paper from the Google team using the Sycamore processor and observing catastrophic events, catastrophic for quantum computation, but actually it may be good to invest if you're watching quantum stocks, maybe invest in mine shafts, right? Maybe they have to go underground to reduce the outside radiation. Or that's literally from the news, the new world record on quantum key distribution optically in China. They also report as one of the advantages the detection of earthquake. If your fiber is so long and the measurement is so precise, that's a new way of identifying small tremors and on a scale which is relevant for geology. So the quantum technology area really need outside-of-the-box thinkers to find applications which are completely maybe unrelated to the initial goal. And that's what's common between quantum technologies and space. We have near-Earth physics, the application of satellites. Those would be those near-term, noisy, intermediate quantum machines that Bob has advertised so much. And then there is what I'd call, and let me be a little bit provocative here, mission to Mars, which is indefinite fault-tolerant computation, which is something that could run Bitcoin cracker with proper quantum algorithms. Right? So before we get to Mars, there is a lot to explore, a lot to gain from. And for the rest few slides, just let me show you other application areas at which we're looking for those individual quanta. So if you have an on-demand precise source, the more precise it is, the more unexpected applications are possible. And one thing, of course, that electrons are quantum particles. They're also waves. And unlike photons, those are waves which feel the electromagnetic environment. They can be ultimate sensors. And that's a joint undertaking, a European research project, when we are the theory node of a network, of building interferometric devices, which would very much fit into the photonics sections, but based on these electronic waves with on-demand pulses and detectors. And let me just give you a flavor. What this is actually the problem that I think day and night, and kind of we are finalizing a next stage in this technology. So this exercise is like having two guns on a Mexican standoff and trying to adjust those such that they hit each other in midair. So I'm exaggerating a little bit, but this is an actual circuit for which our colleagues at the German Metrology Institute have collected the most accurate data, and we are trying to resolve what's the proper theory for this central key element, which is the beam splitter. But the beam splitter, not for photons, but for electrons. And then again, advantage of electrons is that they interact, and that's a nonlinear beam splitter. And those are the beam splitters which are necessary for what Bob has told us about, that you build this huge entangled state out of photons that's built by launching them through those so-called beam splitters. But I think instead of going into this, and that's more technical thing, that's the white paper on these technologies which we've produced, but then maybe that's not that important. I think I'll conclude with a demonstration what happens when a single super-energetic cosmic ray particle hits a quantum processor. Are you ready to see that? That's a real image, that's a real picture, okay? Let's do that. So let's hope the video works. That's what happens. Okay, thank you very much. I'm done.
Thank you.